Okay, so let's get started. So in this presentation, I'm going to talk about my experience with DQMH and how it's evolved over the years, and kind of the things that I've learned and kind of the best practices that I've used while using the DQMH framework. So if you haven't used DQMH before, I would recommend maybe looking at a presentation for an introduction to DQMH. However, this is also helpful because it'll show you the possibilities of what DQMH can do, a small possibility, and where you can potentially take it. Given some ideas. I know a lot of people in here are very creative uh, with creating their own tools and frameworks. So maybe using DQMH in your projects is something in your future. Now, if you have viewed Introduction to DQMH, for example, from Darren Nattinger, you'll notice that he left out a lot of things. For example, he didn't discuss request and wait for reply, did not touch on clonable modules, didn't bring up helper loops. What are helper loops? Didn't discuss private events, anything about module hierarchies, using DQMH with abstraction layers and various other best practices, and other additional tools like anti-doc and TestStandifier. Um, so in this presentation, we'll also be talking about how to use DQMH with TestStand, which is at the very end. So if you are a TestStand user, then you might want to stick around for that. Just a DQMH refresher. A DQMH module is basically the basic building block of DQMH. It's an asynchronous process. In essence, it's a LabVIEW library with a bunch of VIs, right? But one of the VIs called the main VI is the one that is the process, is the item that's constantly in memory, receiving requests and broadcasting data. Now, there's two types of modules that can be created. There's a singleton or a clonable, and we'll talk about use cases for that further on in the presentation. Now, when we make a request to a module, under the hood, we're basically sending firing user events. But the most important thing to know is that there's two types of requests. There's like the requests where you just tell it to do something, and then there's the request where they return data. So request and wait for reply is what we call them in the DQMH world. Um, and there's also broadcast. Broadcast is basically a DQMH module broadcasting data, and someone else, in order for it to see that data, has to create an event structure and register for those broadcasts. So register for an event, basically. Now, when a DQMH module broadcasts, it doesn't care if anyone's registered or not. It just broadcasts. Now, helper loop is basically inside the core of the DQMH module, the main UI. There's an additional loop called the helper loop, and this loop is optional. You don't need to helper loop, but if you have things like that happen continuously, then you might want to put them in a helper loop. To time the helper loop, you can use the event timeout for the event structure. And we'll also show how you can communicate to the helper loop internally from other loops inside the DQMH main VI. Let me just show you a quick demo. And of our demo application for this presentation. So here you will see a VI that has our basic functionality is that it has two power supplies and acquires data from NI CDAC module. So if we start the test, we'll see that we're acquiring data, displaying it on the UI. Of course, this is just a dummy data from a simulated channel. And then we can stop the test. And if we go to on disk, we'll see that it also saves data. So if we open this file, our good old Scout viewer, we'll see that we have the waveform data, and we also have data from the power supply. Currently, we're showing 0, but there's two power supplies, and they're all saved in a single file. So how do we do all this? That's what we're going to learn in this presentation mostly. And through that process, we're going to discover some of the features of DQMH that we can use for this. Stop. Oops. That was a bug in my code. So do that. Let's see. So let's take a look at this main UI. As you'll notice that once we stopped it, the UI disappeared. And that's one of the things that we want to take a look at through the, actually, before we get to that, I'm sorry. Let's go back to the presentation. Now, when we develop a DQMH module or develop with DQMH, there's certain design considerations we have to take into consideration. So we have to think about, will we be communicating with multiple instruments or hardware of the same type? For example, in our program, we have two power supplies. Do we create a DQMH module for each individual supply, power supply 1 or power supply 2? Or do we take advantage of DQMH clonable feature and create a clonable module and then just run that twice? So those are the considerations we have to do. Clonable versus singleton. Do you need a hardware abstraction layer, a HAL, to be created in conjunction with your DQMH module? That's important. You might have already a HAL or an abstraction layer. You can suck that in or use it in your DQMH module. And if you are using classes, you have to think about how you will instantiate your child class inside your DQMH module. What approach will you be taking? Does the module need to run continuously and do something continuously? Then you might need a helper loop. Will the file login be internal or external to the module? This is important because it defines how flexible your module, how modular your module can be. Can you, and also, will you be able to use the logging somewhere else? So if you create a logging module that only does logging and is being called by another module, then that logging module can be reused as opposed to integrating the logging inside. However, in some cases, you don't care about that and you just want the module to do its thing, then you can internalize that logging. Do you need to subpanel the module? Subpaneling means that, well, it will have a user interface. Maybe you're not subpaneling, maybe you're just displaying it. Then again, user interface considerations are important. If you won't be doing that, then the user interface can be just utilitarian. It can provide debugging information to the user, sort of the developer, and troubleshooting, but not necessarily be visible to the end user. So that's important. Will data requests return data from the hardware or read it from a cached value? This is important because depending on the hardware, there could be a delay. The hardware could take some time to return data. So if you need data right away, you might want to just read the cache data. So internally, the DQMH module could continuously read data stored in an internal cache, like a shift register. Um, then, then when you do a request, instead of requesting data from the hardware, it'll just return the cache data. So that's another consideration to think about. Will the module broadcast hardware read data? Again, broadcasting, will it be broadcasting cache data or actual data? Some people and some of you in the audience probably use a CVT, a current value table. So you might not need to get the data via request. You might not need to broadcast the data. Internally, the module could automatically dump the data into a current value table, and then the caller can just get the data from that. So again, these are design considerations you have to think about in your specific use case. I'm going to touch a little bit on API complexity because, of course, creating APIs is a whole presentation on its own. But touch a little bit about on this uh, because the amount of API complexity you create puts more burden on the user of the module and understanding what all the different calls mean and how they're used. So, for example, will you be passing configuration data to the module, or will the module self-configure? That's a good. I mean, that's one consideration. For example, if the the module could read configuration information from a file internally, just read the configuration information and just do what it needs to do. You don't need to pass it information. Will the module automatically start doing its thing, or will you start it by a request? Again, more design considerations. Again, how much burden do you want to put on the user of the module in understanding and knowing how to use it? Of course, that requires more documentation. Uh, as an example, my personal recommendation and what I do is I like to generalize the API into smaller module tasks to allow more flexibility. So, for example, instead of just having a start stop, and internally the module starts acquisition, logs, and then the acquisition stops, the acquisition and the log files stop automatically when you stop the module. So you basically have a start and stop. That's it. Um, I would suggest doing the following: have a start module, start acquisition, start logging, stop acquisition, stop module. A lot more requests, which of course, with the magic of DQMH scripting, is a simple click away. It's not like you're coding all of this. You can just go into menus, create a new request, and just develop all these. And it allows more flexibility and also in anticipation of requests from the user of your system saying, hey, you know what? We don't want to start the logging until event A happens. So it's already there. You don't have to do the extra work. And also by not only implementing these requests, but testing them to make sure they work. So there's that extra layer of development that you have to do. Now, just take a look at our application, and we see that uh, this is just an overview. The main UI for our application is using the JKI state machine, which is kind of my favorite template to use for user interfaces. Um, I know a lot of people use the DQMH module itself as a user interface VI. I prefer to use the DQMH, that's my personal preference. But also, it shows that, hey, you can integrate DQMH with any other code that you have. It doesn't, your application doesn't have to be 100% DQMH, right? And here we see that there are, so the main user interface, the JKI state machine, it starts all the DQMH modules. It embeds the DQMH modules in the UI. On shutdown, it unembeds the modules, and then it stops all the DQMH modules. And the modules we have are three at the moment. We have a DAC module, which continuously reads DAC, and we'll see how that's done. And in line, it logs the acquired data. For the power supply, we have, again, continuously reading the power supply and accepting requests. And the power supply DQMH module is calling a HAL, hardware abstraction layer, with a parent power supply with two specific models. And finally, we have a logger DQMH module, which logs data from both of these modules. Well, actually, we'll see what it does. There's a little bit of trick in here. Uh, so, because if the DAC module logs internally, then how are we combining all the data in one file? And we'll show you how to do that. So this is kind of an overview of kind of the links between the DQMH modules. There's the main UI, which makes requests to the DAC. It also makes requests to the power supply. Internally, the power supply makes some requests to itself. And the power supply logger, as you can see here, is actually is listening to broadcasts from the power supply, and it's logging that. So now let's go into our software in more detail. So in the diagram, again, if you're familiar with the JK state machine, this should be kind of normal to you. But if you're not, basically the JK state machine is a queued state machine, which has a loop, and in the timeout, um, idle timeout case, it has an event structure to handle the user interface portion. I've pulled out the macro initialize and the macro exit to the left of the diagram so you guys can see it while I'm navigating. So if we go to the macro initialize, which just pulls the string and iterates through these are steps. We can see that the first thing it does, well, it does a lot of things, but the ones that are important to us are the start modules. So if you go to the start module, this is how I like to start the DQMH modules. I know there's a kind of a better practice of having the modules that depend or that require other modules, have them start inside of the main VI. But for me, for personal preference, I like to start all my modules in one spot. That way I can organize them, I can rearrange them, and I can put arrows and comments and say, hey, this module has to be started before this module. So I like to put all my start modules at the beginning. Fabiola says, if they are singleton, you can start them in both places. That is true. In other words, if you start a module inside of another module, that you don't get penalized for that. It just ignores it. It's kind of a no-op situation. So here we have the DAC modules being started. Here we have the power supply modules being started. Now the power supply module, the DQMH module, is a clonable module, meaning that every time you start it, it starts a new instance of that module. So I put it in a loop to be able to start two instances of the module. Now, one design consideration you have to think about when starting clonable modules is what do you do with the module IDs? You need those IDs because every time you send a request, you want to make sure it's going to the right module. In order to do that, you need to store those IDs somewhere. Um, so already we see a heated debate here about Fab saying I should start my modules inside, not like this, but that's okay. Um, so the the module IDs are stored in the shift register of my main VI. Now, this example is very simplified. You could have your own design where you take those IDs and put them inside of a class. Maybe typically when I develop applications, I have a system class or one that contains a lot of parameters for the system itself. So you might want to put it into the class, store it that way, so that way you can retrieve it wherever you need it. In this case, I just put in the shift register because we just have the one main VI. And you'll see here that, so it's okay to start modules in parallel. That's actually preferred. It speeds up the loading process. But in this specific case, I want to start the logger after the power supply starts because the logger um, is subscribed to data that is published from the power supply. So I want to make sure the logger and make sure the power supplies have already started before I start my logger. Otherwise, the logger will not um, see the events. I'll just zoom in a little bit here. Okay, so and then we'll go to the stop module, which is kind of the conclusion of this. And you'll see here that I'm stopping all the modules. Again, stopping them in parallel is fine, unless you have a specific reason to stop them in a specific order. And here's where I take out my module IDs and I feed them into the stop module. And here in the macro initialize, we see that we have a embed panels, and in the exit, we have a unembed panels. So let's take a look at that. So on the front panel here, we have some transparent panels, and I'll just color them in so that we can see them. So we have 3 panels, and this is where my UI gets embedded. What is actually embedded? Well, the entire module, the DQMH module, is in fact embedded in these panels. So power supply 1, 2, and then the DAC module. So I use references to these panels, and I pass them into with a request. Now this request is part of the DQMH module requests, and of course it needs the module ID if it's a clonable. And we pass in the subpanel reference, and inside the module is the magic where it subpanels the VI to the panel. And we'll take a look at that as well. And then when we go to unembed, it's kind of the reverse. We take these panels and we unembed them. And it's best practice to unembed the panels before you stop the modules because you get some weirdness where LabVIEW will, close your main app if the subpanels VI stop running, and you get some weird behaviors from LabVIEW. So it's best to unembed things first and then um, close your panel. Now let's take a look inside the module to see how the panel embedding occurs. Okay, so here's my project. You'll see the modules are, let's see here. We have the DAC, power supply, logger, and we'll take a look at the DAC, for example. We'll open up the main VI. Again, the main VI is the core of the module with the loop, and you'll see the user interface of the main DQMH module is the same as the actual interface that was embedded into the main panel. So we'll go up here And there is the embed, and it gets passed down to the message handling loop. We'll go to the embed. Now I've created a sub VI out of this for convenience, and I've created a DQMH template for me because I do a lot of embedding. So my DQMH templates include this VI and this request in the template. And that's another benefit is you can do that. So the code is simply like this. You have to remove the remove the VI, and then you just take the reference of your DQMH module, make sure it's hidden, and then insert it. Now, the reason why we do this is because if you have your DQMH module already open on the side because you're editing code or whatever, it'll give you an error and it won't embed it. So the first thing you have to do is hide the panel and then embed it. And the removing is just a safeguard in case, for example, there's a bug where you accidentally left the previous panel in there, it'll actually remove it. So this is the trick, is to hide the panel first and then embed it. And then when we unembed, it's as simple as that. You just remove it. So there's not that much to it. That's it. Now here, since we're in the DQMH, I'll show you how the DAC happens. So what we do here is we use a DAC events. And this is here because we just want a placeholder for the event. So LabVIEW has a feature where it will fire a user event every time something is acquired into the DAC buffer. So every n sample is acquired into the buffer, and we specify, again, this is just a placeholder. We have a start DAC, and what happens here is we initialize our DAC, and now we're actually putting the DAC reference in here with a specific sample interval. And what this is just taking the event reference cluster, leaving the first one. We don't want to touch the first one. We don't want to touch this cluster here. We want to leave that the same. We just want to update the second one. Because if you see here, the second one is the one that we care about. So that's what we're doing here. And then here we're creating a log file based on the start time of the test. So the file name, so when we start the DAC, we give it the timestamp, and then it creates a TDMS file name based on that timestamp. And then if we go to, there was an actual event called every n samples acquired into buffer. And then that's where we actually pull our DAC off. Okay, there's some questions, I guess, in the comments. Okay, let you guys answer that. So here we have the DQMH reading this. We have the DAC reading the data, displaying it on the UI, and also for good measure, we broadcast this in case we have a use case where we need it. Currently, we don't need it. We're not using it, but we're broadcasting it anyway. So we just created a broadcast with just the graph data. Now, what we're doing here was in the TDMS file, we're using a group name called waveform. So when the data gets saved into the file, it will get saved under the waveform group. And we stop the DAC, we close everything. Now let's take a look at the power supply. And here we have, again, a helper loop. I've highlighted the helper loop in a specific color to show you that it's it is a helper loop and it's something in addition to the base template. However, again, because I use helper loops a lot, I've created a template to include a helper loop. But it's very easy to create a new one. The DQMH consortium menu has a module, add helper loop. So if you click on that, it'll actually add, it'll script and automatically add your helper loop with all the required connections and formatting that is valid for DQMH. So you don't have to create it manually. DQMH scripting tools do it for you. So we have the initialized instrument request, and here's where we do the work to instantiate the proper class. So here we have an enum called power supply model, and inside of here we have the specific child class that we instantiate for that power supply. And then we initialize the power supply and store that class internally in the shift register. Now, this is more of a design choice. Do you put the class inside of a cluster, or do you have the class wire itself naked in the shift register as its own shift register? Again, personal preference. Now, we don't have the benefit here of DAC events. So what we do here is if there's no error, then we specify a timeout of 500. So this wire gets fed back into the shift register, and on the left-hand side, it gets wired to the timeout. And then now this loop will iterate every 500 milliseconds and do something for us continuously. Another important thing to note is after the init, so this is a request and wait for reply. We're not getting anything back except an error. This is important as a developer that you report errors. So if there's an error during initialization, the caller will get back that error. And it'll be the error message that the instrument returned, of course. This is here just for us to see on the screen what class is being used. It's just for the demo. And during the timeout, here's where we have the read data, or read the voltage, and then we broadcast it. Now, it's important in this case for us to broadcast it because the logger that we have is actually going to be reading this data. We have a set parameter request, which basically takes voltage and current, sets it. Again, feedback, error, to know that, hey, this was a good command. Now, one thing to note here as a clonable, if you haven't used clonables, there's always a VI here that determines if the request is sent to itself. Because you have two DQMH modules running, then when you send a request, the DQMH module needs to know, is this request for me or for another module? So this is important to have always. And when you create the request using the DQMH scripting tools, all of this is coded for you. But I'm highlighting it to see the difference between a clonable and a singleton. So if it is addressed, then you execute it. If it's not addressed, then you do nothing. We also have a request to just get data. And in this case, we're actually reading the data from the instrument. Okay. So let's take a look at the logger. Now, this logger doesn't have a user interface, so we're using the built-in default DQMH template because we're not going to be showing anything. And we're not using helper loops. I mean, we could if we want to, if you like that design choice. But in this case, I'm not using it just to demonstrate an application where we're not using a helper loop. The important thing here is to register for the broadcast from the power supply. So this DQMH module depends on the power supply being run. However, because we could have one, two, or even more power supplies, um, we don't know the data the only thing that we know is it's coming from a specific module ID. So that's why we need to use that ID, and we'll see how we're using it right now. We have a timestamp that's coming back, the voltage and current, and we go to the log data case, and here's the log data. If logging is on, and we'll see the request for that, then we basically take this data and we create a group inside of the TDMS file with the power supply name and the ID. Sorry, power supply ID. We could do this even better. Like we can, instead of as part of the data, we can include a specific name. It could be a string, but just for simplicity, I'll just use the module ID. And then, so we use that group for everything when we record it, and then we pass out the TDMS reference. So when you start logging, the timestamp is the same timestamp that was used to start the DAC. So both of these timestamps are identical, thus this log file path will have the same name. So this is how this module and another module can both use the same log file without actually even talking to each other. You just pass the start time and then they both create a file. If you're curious about this, it's very simple. It's just creating a file name based off the timestamp. Nothing special there. And then we turn on the logging because now we're starting it. We initialize the file, we have the reference, and then we can, in the logging, we can use that file. And then when stopping the logging, we just close the file. Is there any questions on this design or things that could be done better? I'm sure there is. One thing I like to show you here is we have the set config, and we'll just set it here. Let's specify 25. We'll see that it's coming back as 25. Let's specify 12. Coming back as 12. If we want to switch to a different power supply, we can actually do that. We don't actually have to stop the module because the core is the class. We can just instantiate a different class, close the existing instrument, instantiate a new class, and then open the instrument. So we can switch this to the BNK, and now we're using the BNK. We would have to reset this because that was for the old, yeah. But that's how you change, okay, you can simply change that. Let's take a look at what we're doing here. So if we go to the event structure, set configuration, you'll see that we specify what we're doing. We're closing the instrument and initializing the instrument. For both supplies. Of course, we can do it selectively if needed. One last thing I'd like to show you on this is when I spoke of self-configuring. So here we have configuration parameters that are read from a file, and we want to make sure. So the helper loop does not necessarily have an initialized state unless we have a specific request to do that. But if we want the DQMH module to self-initialize, then we can read a configuration file and then pass this information down to a special read config file case upon startup. So initialize is here. We can create a private event. Um, we can copy this data type and then tools, DQMH. We can create a save all. That's a convenient feature. DAC, request and wait for reply. Make it private. Load config. Then paste that. Then make this the DAC helper loop. We can target a specific loop, and here's our helper loop. And we get to launch a marketing for DQMH. And here you'll see that DQMH automatically created a private request for us. And now we can take this guy, and we know it's private because it has the little cute little key icon on it. We do that, and then we can wire this up. So now, because it's a wait for reply, we don't have an error. We know that this is completed. Now we can report back that, hey, the module did init because it configured itself. And then we can just bundle that up. And now that configuration can be used. We can also bundle it up here, so we can use it locally in the top loop if we want, like that. And that's how you can read internal data during the initialize and then pass it to the helper loop. Okay, I'm moving on because running out of time here. Okay, so any questions? Okay. So again, modules that depend on other modules. I'm going to skip that. We talked a little bit about that. Let's move on with DQMH with TestStand. Benefits of using DQMH with TestStand, and I have used it in actual applications. It's not just theory. You can take an existing module that you've already created. In this case, we're going to show how we use the power supply module. We haven't made any changes to it. We've used it with the JKSD machine. Now we're going to use it in TestStand. The API tester VIs can be used in parallel to debug your TestStand sequence. If you make the DQMH request broadcast, it makes it even better. There are some challenges, though. The request and wait for reply has a timeout that cannot be aborted by TestStand. Integrating request VIs, well, integrating any VI in TestStand is a pain. You have to do it manually. And clonable DQMH modules create an arbitrary internal number, an incrementing number that's not controlled through TestStand. So we can't predict which clonable module can go to a specific test socket if we want to do that. So there's a tool called TestStandifier, and I'm promoting this because I've invested in this tool. I paid the developer to add specific features to make life easier for LabVIEW developers and using classes, command line interface so it can be run through CLI. And what the TestStandifier does, it validates the DKMH module. It creates a source distribution, modifies requests and replies to add abort capability. So if you hit abort in TestStand, the VI aborts. It inserts a tester into the module's library. That's fine. Creates a PPL. So at the end of the day, you have a PPL that you use in TestStand. And it actually creates a TestStand sequence file with all the calls to the request, which is kind of cool. It maps the VI. So basically, it makes the calls to the VIs. It creates code to launch and sync a module. Creates code to launch and stop the module's tester. We'll see how the tester works. And creates a runtime error callback for the sequence. And 3 files are generated after. So you basically take TestStandifier, you point it to your DQMH library, and you hit go. And it takes less than 5 minutes, probably 3 minutes, and it generates these 3 files: a PPL build log for debugging, a packed library, and a TestStand sequence file. So those two go together, and you can use those and build a TestStand distribution if you want to. Neosoft 2, yes. Thank you, Cyril Gambini, for developing this tool. It looks like you were able to watch the presentations after all. Now let's do a demo. Okay. Any questions so far while we do this? Okay, so now when I came to the realization of this capability, my mind was blown because I don't know if you guys are like me, but I don't really like working with TestStand. I like working in LabVIEW, and of course, if you ask a LabVIEW developer, "Do you use TestStand?" No, hell no. I create my own test execution engine. Um, but if you do have to work with TestStand and you want to stay in the LabVIEW world and do a lot of development in LabVIEW, this is ingenious. So here we're going to start the. Oh, actually, it's here. You can launch the tester from the menus, and it will show up in my other monitor. And this is the API tester for the power supply. This is the same API tester that I developed from a DQMH module. I haven't modified it at all. It still runs, but now it's running in the TestStand context from the PPL. So if I run this single pass, it's always vicarious to run the. Yeah. So now I just did a refresh, and now you can see that there's 4 active DQMH modules running. And if I go to one of them, you'll see that I have data. And I've developed the sequence so that each module has different data. So if I go to 2, you'll see that it says 20 volts. If I go to 3, it should say 30 volts, etc. And here, so yeah, so you can now probe and see what each module is doing while it's being called by TestStand and doing the request. If you make the request broadcast, then you can actually see the broadcast here. For this demo, it slipped my mind and I didn't make them broadcast. But typically what you do is you create a request and wait for a reply plus broadcast. So it's called a round trip, but basically you send the request and then it broadcasts what it did. And then if we let this guy go, let this guy go, let that guy go, let that guy go, you'll see that now it reports here that all 4 modules stop. And actually, while it's paused and it's doing its thing, you can set a voltage, you can get data, you can actually manipulate what's going on behind the scenes while TestStand is running, which is an awesome debugging tool. One thing to note for clonable modules, and I'll show you this one thing in TestStand, is that when you go to the pre-UT loop, here's where we start the power supply module. Uh, if we go to down here, custom module ID, run as singleton false, use default module ID false. If you set this to run state test sockets my index, that is a number that tells you what the number is of the socket. You just have to do a +1, and you use that for the custom module ID. But if you're a fancy TestStand developer, you can specify a specific number for um, the module ID that is for your system. So, but here's just an easy hack to do it automatically, so you don't have to think about it. So now each clonable module will have a predictable ID that you can kind of recall. And that's it for my presentation. If you guys don't have any other questions. And because I built I ran the test identifier. The test identifier has some options where you can allow debugging. It'll actually allow you to see the diagram. You can't edit it, of course, because it's a PPL, but you can actually probe it. So if you have a bug in your DQMH module, which you shouldn't, because you should have debugged your DQMH module before you actually ran test identifier, then this should all work perfectly, and then you pull it into TestStand. But yeah. More info at dqmh.org. You can connect with me on LinkedIn. Let's be friends. Let me look back on this. Oh, source code. Yeah, sure. I'll make it available. I will probably contact the organizers and find the best place to put it. Fabiola is asking, share why I went with DQMH. Okay. Um, I'm the kind of developer that likes to roll my own code. And I've created a lot of architectures in the past. I was I was the developer of VIPM, so I wanted a solution for installing packages. So I wrote VIPM. But um, when when it came to being productive and you know, solving my customers' problems, I realized that I can't spend so much time on frameworks and architectures, and I have to spend more time on solving my customers' problem. And also, I looked around with the different architectures, and the nice thing about DQMH is there's a lively and healthy community, and it's now a consortium, and so it's trustworthy that there are many different companies kind of collaborating to make it better and improve it. And it was basically a stable platform that I felt comfortable working with. Um, so, I mean, I still modify things here and there. I create my own DQMH templates. I come up with my own frameworks using DQMH, but the heavy lifting is done with DQMH, and the scripting tools are great. The socket index +1 is because DQMH has special. Yes. If there's I made a comment to Cyril that, hey, you shouldn't allow 0. Um, but in this special case, but it's there. So yeah, +1 because the index starts at 0, and you can't have 0 though, because 0 is a singleton. That's how you make a clonable into a singleton. Is you just give it a 0, and it'll become a singleton. A few more minutes left here. Yes, Cyril says request and wait for reply round trip. Yep, make it a broadcast if you're using with TestStand. It's free. It doesn't cost you anything. Just do it, and then TestStand, and then your API tester will show all the stuff that actually TestStand is sending, and they'll say, "Hey, this is what happened." Uh, yeah. So again, whether you yeah. So if you for starting modules, I know we have 2 minutes left. Panther Lab, yes. Shout out to Panther Lab. I just didn't have time to put in the presentation. I would have loved to talk about Panther Lab. It's a tool that augments working with DQMH, so check it out. Um, and maybe I'll do another dedicated presentation for that. Starting DQMH modules, my personal preference is to start them at the beginning. Maybe it'll bite me in the butt so many times that I'll change my approach, but hey. Um, Singletons are easier to work with and debug. That's plain and simple. But you know, clonables are more powerful and more flexible. So, but if you want to convert a singleton to a clonable, you can't. You have to create a new clonable and then copy all your code. There is no converter tool. So make your choice wisely, or else it'll cost you in development time. Okay, thank you, everyone. I'm going to be cut off soon. So, hope you enjoyed it. I hope you learned something.